Welcome to the world of material science. My name is Professor Bonnet. In this video, you will learn all about phase diagrams, how to read them, and what can be derived from them. As already mentioned in the last video, the phase diagram is a visualization of the phase transformations of alloys as a function of the state variables temperature T and concentration C. In the thermal analysis method, the temperature of the cooling alloy is measured as a function of time. This results in characteristic discontinuities in the temperature curves at different phase changes, arrest points, which have already been discussed, or breakpoints. Let's take the copper-nickel system as an example. The phase boundaries, and thus the phase diagram, are determined by plotting the break and arrest points of a cooling curve for an alloy into the TC diagram. The cooling curve of pure copper shows the expected arrest point at the crystallization temperature of copper. The cooling curve of an alloy with 25% nickel, however, shows two breakpoints instead of an arrest point. Breakpoints are the result of an energy released during gradual crystallization. More precisely, the first breakpoint marks the start of crystallization, whereas the second breakpoint indicates the end of crystallization. An alloy containing 50% nickel exhibits a similar cooling curve, but with the breakpoints occurring at higher temperatures. The same applies to an alloy containing 75% nickel. The cooling curve of pure nickel again exhibits an arrest point that is typical for pure metals. The small number of measurements taken within the scope of a thermal analysis shown here is sufficient to determine the phase boundaries in such a simple system. The point transferred from the arrest points and the upper break point can be connected. They form the so-called liquidus line, or just liquidus. The liquidus separates the area of liquid-only phases from the area of solid and liquid phases. The points transferred from the arrest points and the lower break points can also be connected, forming the so-called solidus line, or just solidus. The solidus separates the area of solid-only phases from the area of solid and liquid phases. The phase diagram indicates which phases occur at certain temperatures. Above the liquidus temperature, marked by the liquidus line, is the liquid phase, often abbreviated with L. Below the solidus temperature, marked by the solidus line, is the solid solution phase. Between the solidus line and the liquidus line, there is a two-phase area containing melt as well as solid solutions. Thus, the start and the end of solidification, or respectively, the start and the end of melting, can be determined for any alloy A. Moreover, the composition of the phases in the two-phase area at a given temperature can be determined for any alloy. In this example, the composition of the melt can be determined by the point of intersection with the liquidus line, and the composition of the solid solution can be determined by the point of intersection with the solidus line. Besides the composition, the number and the type of phases, the phase diagram also provides information on the quantity of phases in the phase regions. It is assumed that, for example, the mass of B in the solid solution portion, mass M, solid solution, with the concentration C2, plus the mass of B in the remaining melt, mass ML with the concentration C1, at any temperature in the two-phase region has to be exactly the same as in the original melt A with a mass M and the concentration C0. Given the total amount M equals ML plus M solid solution, then with regard to the B content at temperature T, we find that M times C0 equals ML times C1 plus M solid solution times C2. This means that M solid solution equals C0 minus C1 divided by C2 minus C1 times M. And ML equals C2 minus C0 divided by C2 minus C1 times M. If we now label the two lever arms with A and B, we find M solid solution equals A divided by A plus B times M, and ML equals B divided by M A plus B times M. Analogous to mechanics, this relationship is referred to as the lever rule. According to the lever rule, a lever is in equilibrium when the sum of all torques applied to it is 0, so that it is easy to calculate the proportions of the existing phases from the total amount, when the lever arms are none or can be obtained from the phase diagram. Such considerations and calculations are often needed, for example, in foundries. Let's go through a short example calculation. The problem is as follows. Determine the start and the end of solidification, the composition of solid solutions and melt at 1200 degrees Celsius, and calculate the amount of solid solutions and melt at 1200 degrees Celsius for 500 kg of an alloy with 40% B. The points of intersection of the vertical with the liquidus at 40% B show the start of solidification at 1240 degrees Celsius, and the intersection with the solidus show the end of solidification at 1100 degrees Celsius. The points of intersection of the horizontal at 1200 degrees Celsius with the liquidus show a composition of the melt of 30% B and of course 70% A, whereas the intersection with the solidus shows a composition of the solid solution of 26% B and 38% A. To calculate the mass fraction, we apply the lever rule. M, solid solution, divided by M equals A divided by A plus B equals 10 divided by 32 equals 0.313, meaning 31.3%. The mass fraction of solid solution is 31.3%. ML divided by M equals B divided by A plus B equals 22 divided by 32 equals 0.687, meaning 68.7%. So the mass fraction of melt is 68.7%. To calculate the mass of solid solution, we have to calculate 500 kilogram times 0.313 equals 156.5 kilogram. And for ML, 500 kilogram times 0.687 equals 343.5 kilogram. Based on the input quantity of 500 kilogram, we find that for an alloy of 40% B at 1200 degrees Celsius, there is 156.5 kilogram solid solution and 343.5 kilogram of melt. As the composition of the melt and solid solution in the two-phase area changes constantly, unevenly structured inhomogeneous solid solutions are formed from the melt. This is also referred to as segregation. The internal composition of the solid solution is uneven. The center of each grain contains a larger proportion of the higher melting component than the corresponding composition of the alloy. The lower melting component is present in larger proportions on the outside. Looking at our example alloy with 40% nickel, we find that crystallization of the solid solution starts at a nickel concentration of 58%, while the melt naturally contains 40% nickel. At 25 degrees Celsius less, the average nickel concentration in the solid solution is only 51%, whereas the melt is depleted of nickel and only has a nickel content of 35%. Another 25 degrees Celsius lower, the solid solution average nickel content is 48%, and that of the melt is only 28%. At the end of solidification, the average nickel content of the solid solution must, of course, be 40%. The non-directional random movement of particles due to their thermal energy is called diffusion. When unevenly distributed particles move from areas of high concentration to areas of low concentration, this causes a mass transfer resulting in a concentration equilibrium. While a concentration equilibrium is reached quickly and easily in the melt, it takes much longer in the solid solution. Here, the predominant mechanism is a change of position with adjacent voids, as a change of an atom to an interstitial site would require much more energy. At technical cooling rates, the equilibrium cannot be reached. This results in unwanted segregation effects, referred to as liquations. In general, alloys with narrow two-phase regions are less prone to segregations than alloys having pronounced two-phase regions. The properties of an alloy with solid solution cannot be calculated from the properties of the components because the lattice distortions do not change in proportion to the concentration. The strongest lattice distortion is in substitutional solid solutions when each component occupies about half of the lattice sites. For copper-nickel alloys, the tensile strength determined in the tensile test shows a corresponding maximum at slightly more than 50% nickel. Due to the introduced additional lattice distortions, the tensile strength of this alloy is higher than the strength of the two components. Quite similar is the hardness, in this case measured according to Brinell, which in any case is roughly proportional to the strength, as we will see in the coming video on time-temperature transformation diagrams. Even if the elongation at break A 5.65 decreases with increasing lattice distortion, the increase in strength over solid solution hardening does not lead to such a drastic embrittlement as we have seen, for example, in cold work hardening due to the introduction of dislocations. As always, I'd like to thank you for your attention. I hope you will also watch the next video in which we will continue to discuss the interesting topic of binary systems.